one can define functions and declare types in Haskell. What we want is, of course, to be able to use these to write programs that can interact with the environment. So we need to have notions of input and output as well. I happen to have written a small program that does exactly that. And if you want to run an actual program in Haskell that interacts with the environment, you have to do that through the command line. So here I am at my command line. I have a program that I want to run. I do that using run Haskell. And the program's called What's My Name? Let's see what it does. What's your name? Well, that's my name. Did you know that your name is Sna, spelled backwards? No, I didn't know that. Would you like to repeat this very meaningful interaction? The program asks me. If so, type yes, and yes, of course I would. What's your name? The program asks. Let's give it my initials just for fun. Did you know that your name is HH, spelled backwards? Well, in fact, I knew that. Would you like to repeat this very meaningful interaction? If so, type yes. I guess I don't really want to, so I type no. And that's the end of the program. How can you write things like that and things that are much more advanced than that in Haskell? Let's have a look at that just now.
Now, in this part of the podcast, I'm going to talk about input and output in Haskell, because if we ever want to write a real program in Haskell, and of course we do want to write real programs in Haskell, then we have to be able to make the program communicate with the outside world. And at first this might seem dubious, because Haskell is a pure functional language and there are no side effects. There's no notion of state. But if we think about input and output, they're usually thought of as operations that can change the program state. And how can we handle that? I'm going to tell you now. And what I'm going to describe in the following is a special case of a more general notion in Haskell, which is that of monads. Monads they're a very nice notion because they allow us to describe stateful properties of programs in a purely functional way. But for now, let's stick to I/O. Now, in order to understand how we can think of I/O actions as happening in a pure world, then what we should think of an interactive function as is as a function that takes the current state of the world as its argument and gives us a modified state of the world. In the old world, A was not written on the screen, and in the new world, A has been written on the screen. So the type I/O should be the type of functions from world to world given some suitable world type. And expressions of this type would then be called actions, and they can be composed. Actually, we have to make a slight modification because programs can produce a result of some type. So in fact, we would want I/O actions with some type A. So we would want type IOA, which would be the type of functions that take a world as argument and then return a pair consisting of some value of type A and a new world. So these are our I/O actions, and they can indeed be composed. I'm now going to describe three basic I/O actions that can be used to build more complicated I/O actions. The first one is an input I/O action that allows us to input a character from the keyboard. It's called getChar. It reads a character from the keyboard, echoes it to the screen, and then it returns the character as its result value. So this is an I/O action of type IOchar. This is a primitive of the Haskell system. It's built into the Haskell system, and so is putchar, which is a dual. It's the output action. It writes a character to the screen and doesn't return a result value. So its type is character to IO parentheses, and parentheses here is the type of tuples with no components. This is what we use to say that we do not return a result value. And putchar is also built into the Haskell system. Now the final I/O action that's fundamental to Haskell is return. And return turns a value into an I/O action, and this is useful when we want to finish a sequence of actions and say, finally, here's a value. So return is a function from A to IO actions of A. So that's all it does. It turns a value into an IO action. And of course, many of you are lovers of C-like languages. So here's a warning to you. This is not a return value statement. There are no statements in Haskell. It's just a construct that encapsulates a term and says, this term is now an IO action. We can compose IO actions as sequences. We can use a do notation to turn IO actions into a composite action. And typically, we would do this by writing the IO actions in this way. A1 up to AN are IO actions. V1, left arrow, A1 means that the variable V1 gets its value from the IO action A1, typically by some return. And likewise for the other IO actions, VI from AI. They're called generators, just as in list comprehension, so it's no coincidence that the notation is the same. In both cases, the generator tells us where the variable VI gets its value from. And here it's from the IO action AI. Now, we can use the IO actions together with composition to create composite actions, as I've just said. Here's a very useful example. Suppose I want to read a line from input. How do I do that? Well, we compose some IO actions. The first one says, here's a character. I get the first character from the keyboard, and it becomes a value of W. If W is end of line, we finish the sequence by the IO action return the empty list. Otherwise, we compose with more IO actions. The variable XS gets its value from getLine prime. In other words, we call getLine prime recursively. Once that has been accomplished, we return W up here counts with XS. So in this way, we see that we can read a line by reading every single character and finish by an end of line. So from this, we get a composite action that reads in a line of characters from the keyboard. This is actually built into the Haskell prelude, so we don't need to do that. We don't need to write it ourselves. It's there already. Let's see how this works out in practice.
Now here is our getLine function that we just mentioned, and I have also defined a main that actually uses getLine. We call getLine prime here, we bind the result of this input action to Z, and then afterwards we use the output action put string line to put the line you wrote concatenated with the value of Z to the screen. Let's see what happens. First, let's load this into Haskell. Haskell is happy. Now let's call main. And let's type in something. You wrote something, the program says. So this is what we can do with getLine prime. Of course, we don't need to define getLine prime. getLine, as it's called, is already in the standard prelude of Haskell, so we can make use of that. I'm now going to talk briefly about how we can input content from files and output content to files. And I'm going to write a tiny program that will read lines from a file of animal names. Here it is, animal.txt, horse, cat, dog, mouse, rabbit, manatee, and rhinoceros. Eventually, I will write the name of my favorite animal to a file called favorites.txt. My favorite animal happens to be the manatee, so I would like to output this to a file called favorites.txt. In order to manipulate files in Haskell, we need the module system IO, so first we're going to import that. I'm going to write a sequence of IO actions that do what it is I want to do, have done. So the first thing I do is I want to open the file animals.txt, and I want to open it in read mode and in Haskell. This means setting up a file handle. So first I create a handle called myHandle, which gets its value from the function open file that takes a file name and a mode, which is a read mode here, as its arguments. So I have now set up a file handle. After this, I want to read the content of the file that's handled by myHandle. And to this end, I use the function hgetContents. What is the type of hgetContents? Let's have a look. Oh well, first of course we need to import system.io. Got that. So let's find the type of getContents. It's a function from handle to IO string. So this function takes a handle and returns an IO action of type IO string, and this string is then bound to my animals. So when we read a file, we get a string. Of course, we often want to split up the string into a list of lines. I'm going to make use of that now. I would like to print out the first animal in my file. So what do? I call the function lines on my animals, and what's the type of lines? It is string to string list, so I get a list of strings. I index this list, I get the first element of the list. I do this by indexing with 0. The first line in my list of lines has index 0, not 1. This value I call SOMEAnimal, and next I put SOMEAnimal to standard output. Afterwards, what do? Well, it's time to output content to my file favorites.txt. So I create another handle, which I call my other handle, and I open the file favorites.txt, which need not exist. It doesn't exist, in fact. I open it in write mode, and afterwards, once I've done that, I take the lines of animals, I index it with 5, which means I get element 6, because the manatee, which is my favorite animal, is at line 6. So I index with 5, and then I use the function hputStringLine. Let's see what the type of that is. It's a function of type handle to string to IO. So hputStringLine takes the file handle, it's my other handle, and it takes a string, which is this string. And what do I get? Okay, so this is our program. It's been loaded into Haskell. Haskell's quite happy. Let's try to evaluate main. We expect main to first get the content from animals.txt via the file handle, and then we use the lines function to split the content of my animals into lines, and then we take the first element of this list, which has index 0, confusingly perhaps, and the first element of the list corresponds to the first line of animals.txt, which is horse. So I expect to get a horse. Let's evaluate main. Wow, we got a horse, isn't that nice? Let's see what we have in the file favorites.txt. If everything goes as expected, we would have a manatee. Where would we get the manatee from? Well, we create another file handle, my other handle. We then opened the file to this handle. The file was favorite.txt. We opened it in write mode, and we put to my other handle, the element in the list of lines with index 5, so that's the 6th line. That should be the manatee. Did we get a manatee? Let's have a look. So we're going to open favorites.txt. Oh, this is tiny. Let's see. Oh, yes, it is a manatee. So this works fine, just as expected.